All right. Hello, everyone. Thank you for tuning in to today's installment of the Corundum developer meeting. Let's go ahead and get started with the status updates. Right. So I got quick announcements and then status updates for today. So the next Corundum developer meeting will be on. Wait, did I get these mixed up? Sorry, I got these dates switched around. The next Corundum developer meeting will be on the 14th. The next Switch developer meeting will be on the 7th in a week. All right. So let's go over the status updates real quick. I've been working on the Mac control and PFC components. I don't have much new to report on that, but we'll go over that briefly. And then kind of to support that, I've been making some modifications to some of the FIFO components used in Corundum, as well as some updates to the Verilog Ethernet repository as well. And then I also just got a new board recently, one of the SN1000 boards, which seems to be identical to the new EU45N. I think they just kind of did a marketing rebadge sort of thing. So at some point, I'd like to get Corundum running on that, but there's a couple issues that need to be sorted out, which might be of interest to the community in general. So more on that in a minute. All right, so Mac control and PFC pause frames. For those of you not aware, I mean, I think everybody on here is going to be aware of these, but the Mac control layer is for exchanging, Mac level control messages just between ends of the link. They're not supposed to be forwarded by switches or interpreted by the, networking stack sitting behind the Mac. So these are mainly used for PFC and pause frames. So PFC is a priority level flow control setup that allows you to pause individual priority levels, and then pause frames just pause the flow for the entire link. Right, so I've been working to implement these things in HDL such that they can be used either in the Verilog Ethernet repository, just in the Macs, or integrated into Corundum. So I've tested the implementation so far in hardware in the Verilog Ethernet repository, just attached onto gigabit and 10 gig Macs, and everything there seems to work just fine. And currently I'm working on the integration into Corundum, where what we need to do is integrate the actual Mac control layer code in either with the Mac, so I just need to turn it on, or integrate it deeper in the data path, kind of in a more Mac independent way. I might end up doing both, but I think for now I'm going to start out with the implementation of the Mac. And then I also need to make some modifications to actually generate some of the necessary signals. So terminating pause frames is not really a huge deal, or terminating the pause request is not a big deal because you just need to block outgoing TX traffic. But dealing with PFC requires implementing traffic classes in the data path in various points, and actually generating pause frames requires feedback of the depths of some of the transmit FIFOs. So I'm going to take a crack at getting that working first, but obviously there's a few things need to be implemented along those lines. So that's the current status there. Now, in terms of the FIFOs, there's a couple of modifications that I've been working on here. The first one is for generating pause frames. We need to be able to track the FIFO depth, so we need to add depth status outputs to the FIFOs, because that would make a lot of sense. There's probably a few other use cases where that would be handy. But for the frame FIFO, it's actually slightly non-trivial because there's 3 different pointers that are used, and as a result, you can define basically 2 different depths. So either you can look at the kind of active read and write pointers and determine how much data is currently sitting in the FIFO, but some of that write data could be part of a partial frame that hasn't fully been written into the FIFO yet. So there's an additional pointer that's kind of the committed write data into the FIFO, and that one will advance whenever a complete frame is written into the FIFO. So you can also look at just kind of the write data that has been committed to the FIFO. And making both of these available probably would make sense because the semantics are slightly different. With the old implementation that I had for the frame FIFO logic, the logic wasn't particularly clean for a couple of reasons. I'll have a little bit more on that in an additional slide. So what I did is I refactored basically both the async and the sync FIFO modules to clean up the pointer handling, make things a little bit more straightforward, and clean up the synchronization code and a couple of other things, such that I could get the such that I could, well, not only clean up the FIFO logic, but also by cleaning up the pointers, it makes it a lot easier to compute these two different depth values. So for the synchronous FIFO, we report those two. For the async FIFO, I actually compute both those values in both the input and output clock domains. So wherever you need it, you can just wire up to the port and have access to that. I'm also thinking about adding two other minor features to the FIFOs. One of them is pause support, so you can actually terminate, the pause frames just by asking the FIFO to stop sending. That doesn't require much additional logic to do it, and integrating that into the FIFO, it seems like a relatively logical place to do that. And then also I'm going to finish up the support for what I'm calling pseudo-elastic buffers, which requires just a couple little additional odds and ends at the FIFO level for that to work. So more on that in a moment here. All right, so just taking a look at the changes that I made to the async FIFOs, or to the, well, both synchronous and the asynchronous FIFO, in terms of handling in terms of running in frame mode, we use three different pointers. So the old setup, it uses the right pointer current, and the read pointer. And basically the way I wrote it is that either the right pointer or the current right pointer is used to actually write the data into the internal blockgram, depending on the mode. So that makes things a little bit complicated because we've got two different synchronization techniques that have to be used depending on whether you're running in frame FIFO mode or regular mode. And just the way I put that together was kind of messy. And one thing I realized is that if we want to compute, both of these different FIFO depths, we actually need to have both of those values synchronized using both of the synchronization techniques. So it doesn't make sense to try to do some harebrained hybrid thing, which will use one technique or the other depending on the parameters. It would make sense to have just two completely separate paths using different sets of registers. So I did some ruminating on that, and I realized, well, what actually makes sense is to have a right pointer and a read pointer, which are just always used for accessing the blockgram, and then have a right pointer commit, basically, which is updated whenever the data is committed into the memory, which for a normal FIFO, it's committed, every cycle, but for frame FIFO, it's only committed at the end of the frame. And then the read side always looks at the commit pointer. And then you can synchronize the right pointer with standard grade code sync, and the commit pointer that has to use a handshake sync. Has to use a handshake sync because it doesn't increment, it jumps. And I found out the hard way that you can't use grade coded sync for that, because if you have if you're feeding a Mac or something, and that will occasionally the FIFO will think it's empty and it won't produce an output cycle in the middle of a frame, and then the Mac gets confused and the frame gets dropped. And yeah, that was fun to debug. So yeah, use a handshake sync now, so that's not a problem. So with both of these paths available, now it's possible to implement both depth status signals in both clock domains. So both source and the sync clock domain will output the current kind of approximate FIFO depth, both for just raw data and for the committed data. So that change has been made. And then the other two changes that I'm looking at here, I'm going to add a little bit of logic to support pausing the output of the FIFO. And the idea here is that this will support frame level pausing. So if you assert the signal saying, please pause the output, it won't actually do anything until it has reached the end of the current frame, and then it'll pause and prevent the next frame from being sent. Doesn't require much additional logic to do that, and the FIFO, I think, is a logical place to put that, just because you're probably going to want to pause stuff when moving between different components. So, and you usually use FIFOs to connect different pieces together. And this would be super convenient not only for pause frame termination on the transmit path, but also to drain the receive data path as well if you want to make any changes potentially to components in the application section or whatever. And also, occasionally there have been some issues with Corundum and various corner cases during the driver bringing the link up or bringing it down. So being able to turn off the flow of traffic at the port level would potentially be useful at avoiding some of those problems. And then the other change I need to make is in relation to what I'm calling pseudo-elastic buffer support. So basically, the idea is to have a frame FIFO, but with slightly different semantics. Basically, we can't drop invalid frames, and oversized frames are forwarded when the FIFO is full as opposed to dropped. And the idea with this is it allows a much smaller FIFO to basically do the same thing as a frame FIFO would otherwise. The reason this is necessary in Corundum is because I want to have a large kind of shared FIFO module which can handle the various traffic classes as well as multiple ports. And that'll be connected to the ports through asynchronous FIFOs. And having asynchronous FIFOs that can store, multiple jumbo frames ends up eating up a lot of block RAM resources somewhat unnecessarily, and also increasing the latency. So if we can replace those with something much smaller that maybe uses distributed RAM, then that would be good. But the problem is, at least in the TX direction, you have to make sure that the frames are presented contiguously to the output MAC. Otherwise, the MAC will drop the frame. It'll end up in an underrun condition and drop the frame. And then in the receive direction, you also have to make sure that you never deassert the T-ready input. And if there is an overrun, then the frame has to be dropped or marked to be dropped, one or the other. And the reason I'm calling this a pseudo-elastic buffer is because it's kind of going to serve a similar purpose as a normal elastic buffer that you might find kind of as part of the Ethernet PHY layer, but it's working at the level of AXI stream with frames instead of inserting and deleting idle control characters. So it's not quite doing exactly the same as an elastic buffer, but it serves kind of a similar purpose because the idea is to maintain in the TX direction to maintain kind of a minimum fill level to make sure that you're not going to have a buffer underrun by the following component, as much as possible. So, like I said, it works similar to the existing frame FIFO, but the idea is that when you have a frame that's larger than the FIFO size, it will forward the frame through instead of dropping it. So this does mean that if you have a big gap on the input side, then you could run into a buffer underrun condition. But if you don't have a big gap, or you only have a few small gaps, then you should get similar behavior to using a proper frame FIFO that stores the whole frame first, because it'll be able to transfer the frame out contiguously. There is one feature that's missing that I need to implement, and that is on the RX path to properly handle overflow. So right now, if you don't set that up correctly, basically the MAC, it doesn't have an input for the T-ready line. So if the FIFO fills up, the question is, what do? Previously, with the frame FIFOs, if you get into that condition, then it'll drop whatever frame won't fit in the FIFO. But if we're not storing the whole frame in the FIFO, then you can't do that. So instead, what we need to do is add some additional logic to the FIFO, where if you do get to that overrun condition, it will mark the frame as bad by setting the bit in the T-ready signal instead. So not really a complicated piece of logic, but that's an important component in terms of being able to make these TX and RX FIFOs a lot smaller. So I'm going to start chipping away at that, and we'll see how that goes. All right, and then I made a couple changes to Verilog Ethernet. One of the things that we're working on at UCSD is building basically an FPGA-based switch. So in order to get more ports, we have these modules from High-Tech Global that have 6 QSFP28s on them that plug into an FMC Plus. So you can use that on the VC118 or on the VCU9 or the HTG 9200, and potentially a few other FPGA boards that I don't have. So those are the only two that are in both Verilog Ethernet and, well, I guess the HTG 9200 is not in the Corundum repository yet. This doesn't really make sense to run Corundum on that one in its current form. But we've added reference designs to the Verilog Ethernet repository for these two boards that include this additional FMC Plus and turns on a lot of ports. So with that one, you can get 8 QSFPs on the VC118 or on the HTG 9200, which already has 9. It brings it up to a grand total of 15. So that's a lot of bandwidth and a lot of Macs. I've also worked to integrate the Mac control and PFC pause frame support to all of the kind of core Mac modules. But the wrappers are to-do. So all of the Mac with FIFO modules needs to be done there. I think also the GMIIR, GMII, MII wrappers that include the PHY interface components. That's also, there's still some work that needs to be done there. Let's see. And I think the work there is mainly in terms of just bringing the test benches and stuff up to snuff in terms of getting the PDP tests operational. So shouldn't take too long to get that finished off. Another change that I made is a procedural generation of the sources and sinks in the test benches. So especially with the HTG 9200 plus the QSFP adapter, that ends up being a lot of sources and sinks. So if we can generate that with a couple of for loops, it saves a lot of code. That's now implemented, and I've also backported the same change effectively to Corundum as well. So all of the top-level design test benches have gotten a bit shorter. Let's see. And then that brings me to new board support. So like I said, recently I got an SN1000 board, and I've also figured out that I believe these are identical to the U45N. It seems to be just kind of a new SKU, new part number, rebadged version of the SN1022. If you look at the OpenNIC repository, they literally have a commit that renames, the SN1000 to the U45N. It just switches all the code over. So I think that they're basically the same thing. So it would make a lot of sense to get things running on one or the other. So the interesting thing about this card is that it has the 56G PAM4 SerDes, which Xilinx calls GTM. So one of the two ports on here can do either 4x25, 2x50, or 4x50. So, 200G on one port is potentially kind of interesting. And this also has the hard, this is not a Zinc device, but it has a separate chip on the board, which is some sort of ARM CPU. I don't know too much about its capabilities, but it has at least a PCI Express link to the FPGA and potentially another connection as well. I'd have to double check. I recently acquired one of these boards, but they have a proprietary JTAG connector, which is this 60-pin edge connector, 0.5 millimeter pitch for JTAG and some other debug and status signals and whatnot. So in order to actually get Corundum running on this thing, I'm going to have to somehow get a JTAG cable connected. So I'm wondering, is there anybody else that's interested in helping to make a generic Alveo JTAG adapter? The idea is to spin a little custom board with one of the FTDI FT4232HL chips, which with some tinkering in the EEPROM can interface directly with Vivado. And then we'll toss on a 14-pin connector, the standard Xilinx JTAG header, a 30-pin for a U50, and one of the 60-pin headers for the U45N/SN1000. So be a little board that could be used for multiple different Alveo boards instead of having to pick up various adapters from Xilinx. So I have one of the adapters for the U50, so we could certainly probe that as well as the U50 itself. And somebody on the Corundum Zulip actually had the complete schematic for the SN1000, so we know what all those pins are. So it's just a question of, making sure we have the U50 pins correct, and then spinning a little board here. So if that's of interest to anybody, let me know. I would be more than happy to take a look at your schematic and make sure everything looks good. Otherwise, maybe I'll look into doing that some point in the near future. Because once I have that, then I should be able to get Corundum running on this and get support for that upstreamed. But without that, I can't really do much with the card. So I think that about rounds it out for the status updates that I have for today. So at this point, if anyone has any questions or comments, fire away. Nobody has any questions or comments about anything? Or anything that you want to discuss in general, just in terms of Corundum? I know there were a couple people asking about RDMA support. I forgot to put a slide together this week. I guess I should do that for the next time, just to summarize where we are in terms of if we want to support RDMA at some point. What needs to be done to get to that point. If anybody's interested in that, we do have there should be an RDMA channel. I will double check on that. Oh, we have a couple different RDMA channels. Yeah, well, we can certainly pick that up on Zulip and discuss RDMA, just to make sure that if anybody wants to help with that, anybody else is interested in that capability, that that we can work to make that happen. All right. Well, if nobody has any... Oh.
No. Well, don't really have anything. I've been trying to hang on the whole time, really, listening all the various updates that you've put into it. You really have to be good into that field to understand what's going on. But congrats.
Yeah, I've been pretty out in the weeds with some of this stuff. Yeah.
Right. Right. It's a cool thing also that this is being actively developed, considering there's a good number of other softniks out there. But for a good number of them, it seems like to get a paper published and then development sort of stops. No, somebody's not
right.
It's
well, I guess that's one thing about Corundum, is that the goal of the project isn't to build Corundum; it's actually to build a tool to support a different research project. So,
right.
We need to get the functionality for this other research project to do what it needs to do. So, yeah, that's
okay. Topic of which remains secret.
Well, I mean, I don't really talk about it because it's not super relevant to Corundum, but I certainly can talk about it. At UCSD, we're doing a bunch of data center networking related research that involves optical circuit switching. So one of the things that we've been trying to do for the past quite a few years is figure out how to actually connect one of these switches to servers and run some kind of application through that setup. That's kind of the holy grail. Hey, can we actually run an application on top of one of these experimental networks? But no commercial networking hardware is built with circuit switching in mind. So turns out with circuit switches, when you send stuff is incredibly important, because you're reconfiguring the links optically. So if you send a packet at the wrong time, it either gets lost completely or it goes to the wrong destination. So in order for that to work, we have to be able to precisely control when stuff is sent. And if we're talking about kind of a microsecond time scale, you can't do that with software, and you can't do that with existing NICs. It's requires too much precision. So what we've ended up doing is building Corundum, and then we can modify the schedulers and whatnot in Corundum to support the operation at the time scales that we're interested in. So
Okay.
we need Corundum for that. And well, all you guys get the advantage of the rest of the platform, even if you're not doing precise timing stuff.
Okay. Well, it's not stated that the whole genesis behind the project was really controlling sending time at a microsecond scale, right, or nanosecond scale. So yeah, just a lot of seeing where this all started
it was
from.
like we wanted to do that, but we can't do that with the existing hardware. So okay, well, let's build our own darn NIC and make it work.
Yep. 2 years later.
Yeah, pretty much.
Okay.
But yeah, once we got it working, it's like, well, I think there's a lot of other people that could take advantage of just the NIC capabilities of this thing. So we decided to go ahead and make it open source, and well, here we are. But yeah, if that can be useful for P4 stuff too, hey, great.
Yep. I think it will be.
All right. Well, I mean, if we run out of stuff to discuss, then I guess we can go ahead and adjourn for today and pick this up in a couple of weeks. Well, unless I don't know, is there anything from MLE's end that needs to be discussed? Joachim, anything you guys want to bring up? Sounds like probably not, since
No, not really. But thanks for asking.
okay.
So yeah, I can say that we are at least one group which is interested or would be interested in RDMA stuff.
Right. So I think you guys reached out to me, and then
no news.
yeah, I also heard from somebody else who's going to be doing some work on Corundum over the next few months or so. Might also be interested in working on some of that stuff. So yeah, I mean, the big thing is not just people that are interested in using the functionality, but potentially interested in helping to build it. So if that's the case, then yeah, we can certainly coordinate on that and try to figure out what needs to be done and go from there. So yeah.
Yeah, sounds good.
All right. Well, if we don't have anything else to discuss, then like I said, we can go ahead and adjourn for today, and I'll see all you guys in 2 weeks on what is that, August 14th, right? Let me double check on that. Yeah, August 14th. Geez, we're already out of July already. How time flies.
Don't remind me.
All right. Well, I'll see you guys later then.
See you later.
Great.
Yep.
Thanks for tuning
Thanks,
in.
everyone. Thanks, Alex.